Okay, hello Internet. What's going on? So, it has been a long time coming. I have a series of CTF videos, but this video is a summarization of a book that I've recently finished. And this book, as you can see, is all about container security. And a little bit of context around this book is I'm a part of a book club at my company that I work at. And it's one of the books that I've found the most practical and has the most substance in the areas that I'm the most interested in. That's what I would say. So anyways, this is the book, and this is the author. Her name is Liz. And what I'm going to do here, instead of basically regurgitating the entire book to you, what I plan on doing is basically pulling out the bits that I found the most interesting or the things that I felt were the most specific to containers. There was a lot of stuff that I learned because I'm kind of new to this whole container and Kubernetes space when it comes to security. So this is all kind of like is new to me. So there's a lot here, and I'm not going to try to, like I said, regurgitate the whole book. So we're going to try to, keep it tight, and hopefully semi-short. So that being said, here's the agenda. So first things first is we're going to talk about the ingredients that make up a container, which is surprisingly simple in the kind of the theoretical idea of how it's made up. And interestingly enough, a lot of the ingredients, and actually all the ingredients that make up a container, the basics of a container, have existed for long periods of time. And really the main reason why it's come to fruition today is that the implementation of these different old elements have been put together in an interesting way, but also it's been put together at the right time where cloud technology is prevalent everywhere, and containers are very useful in a world that we live in where technology has basically gotten to the point where it's cheap and scalable, and it's basically outsourced to big cloud providers. Next thing is the difference between containers and virtual machines. There's a lot of answers and videos and articles you'll see that discuss the differences between the two. My goal within this section is not necessarily to talk about what they've talked about, because you can find that elsewhere, is to talk about the specifics that I found interesting that seemed not obvious to me when I read through it. So hopefully I can get some nuggets out there for you. Securing containers, this is going to be the big chunk of this whole entire agenda, really is talking through some of the specific things that I thought were interesting and different for securing containers. There's definitely some things in there that are discussed elsewhere in securing other items that aren't containers. But I wanted to kind of focus on the things that I thought were very specific to containers and also things that were interesting and new to me. Next is, like I said, this book there was a lot of new stuff in there for me, and there's a lot of stuff that I want to dive into in the future. So I basically have a few items here that I've not talked about in this topic or in this summarization of this book that were important for the book, but I didn't want to basically have a 4-hour video. So it's a maybe next time section. So we'll talk about those maybe next time. And as per usual, we have resources. So I have a list of resources that I found useful that were outside of the book. So they weren't resources from inside the book. Well, some of the resources were linked in the book, but these are outside things. So lectures, webinars, articles, and things like that I'm going to link at the end that I will put in the description of this video so you can watch if you're interested. Well, with that being said, that's the agenda, so let's get started. First things first, ingredients. So the three main ingredients that I found that seem to be consistent along a lot of what people are discussing, what make up a container. The image piece, the third one here, is semi-debatable, but the two here that I would say are the main pieces that make up a container, at least the basics of a container, are Cgroups here and Namespaces. We'll include images because, like I said, there's a few different people that I've watched and read about that talked about images being a third ingredient that make up a beautiful, cute little whale, which is our container. So with that being said, let's start with Cgroups. So what are Cgroups? Let me go back actually. The way I thought about simplifying these two items of Cgroups and Namespaces is you can think of Cgroups as the ability to do something, and you can think of Namespaces as the ability to see something inside of the container that you're sitting within. So you're sitting inside of a container, right? And you can only do and see certain things because it's obviously isolated. So with Cgroups, I see it as kind of the arms and legs of the container, the things they can do. And with Cgroups, you can actually segregate certain sections of a kernel and of a host machine and say basically within this host machine, this container is limited to this amount of CPU usage and this amount of memory and these different items that are associated to resources. So that's kind of the main process or the main kind of idea around Cgroups. Now, within the book, she actually talks a lot about the importance of Cgroups and how they're leveraged to prevent certain types of attacks. And what you're seeing here is a thing called a fork bomb. And a fork bomb is probably one of the coolest names I've ever heard of when it comes to an attack. So this series of characters I've seen tattooed on many different body parts on Google Images, and there's a lot of merch associated to this as well. So what we're looking at here is basically a simplistic fork bomb. And there's a good explanation to this that I found on a website that I forgot what it's called, but I'll link it below, obviously. And in there they basically break down this syntax and talk to you, basically explaining what's happening here. At a high level, from my understanding, is that basically we have a function calling itself twice, and it calls itself twice on every single call. And when it does that, it's unable to, I guess, terminate itself. So it continually keeps, forking itself and expanding like a virus. And as you can see here is a simple image that I got from Wikipedia that basically has, a function being called, that bomb explodes, then it forks itself, explodes, forks itself, and it keeps doing that. And all the resources get sucked up inside of that container. And if we're able to basically suck up all the resources in the container, it's similar to a denial of service attack. So Cgroups come in handy here because we can actually segregate and say you're only allowed to use a certain amount of resources. I'm going to put a video overlaid on top of this video of Liz, the author, showing in one of her presentations that I watched, her actually creating a fork bomb and leveraging Cgroups to prevent that fork bomb from actually impacting the machine that she's running inside of. And the specific video I'm going to show, some context to that, is that she set the container to only allow it to run 20 processes. And of those 20 processes, once it exceeds that, then it stops it from using any other additional resources. So here's the video. Hope you enjoy it.
Okay, so what did that mysterious set of characters do? So we're going to define a function inside the shell called colon. And inside that function, we are going to call colon. We're going to pipe the results of colon into colon, and we're going to run that in the background. So that is just going to keep creating a lot of processes. We have to remember to invoke it the first time by running colon. The anatomy of a fork bomb. Right, are we ready? Okay, so that is trying to create a lot of processes. And if we look on the host at what's going on, we can see there's some shell processes and some defunct shell processes. But there aren't that many of them. It's not gone crazy. This is, I think we have successfully constrained the number of processes to 20. However hard that fork bomb tries, it can't exceed that number of processes.
So now, after Cgroups, we're going to go to Namespaces. So like I said, Namespaces is what you can see from the container. So there's different types of namespaces. So here I've mentioned out a few different items here, a simplistic kind of showing of different types of namespaces. Specifically, I'll show you a few. So this one here is a namespace for what you can really see inside of a directory. So inside of the book, Liz talks a lot about a few different items here. One thing with this namespace here is it's called jailing. So you're jailing your directory. So what we're going to do is we're going to draw, oh no. So here, let me grab this. This is our jail cell, and you're locked in. It's your sad face. You're locked inside. That's a horrible drawing. So what we're doing is we're jailing a directory inside of the host, the outer host here. So this is our outer host, right? So this is the actual root directory here. And then what we're going to do is we have our change root. So we're going to run change root, which is basically saying that we want to change the root of the container that we're working in. So it's a fake root. It's not the actual root. And you can see that it states here as fake root. So our root is going to seemingly be here, but that root is actually going to be linked back to this change root here. So it's not the actual root, but it's our virtual root. And there's a few important things here. So like I said, it's called jailing the directory. That's what the terminology is. Important things here first. So change root is what I mentioned, but Liz mentioned that the more modern way of doing this is running pivot root. I've not run this or researched it, but probably will soon. In addition to running this, there's another thing that she mentioned that's a good practice to do is actually to do unshare and also -- fork. So unshare and -- fork are basically two items you want to run when doing the change root of the directory. So you're actually completely separating and segregating the parent process from the child process, which is going to be our container. And if you don't do this, what's going to happen is that you think that you've separated them with the change root, but actually in all reality, the child process is still running in association to the root of the parent. So they're not securely separated in the way they should be. So running unshare, so you're unsharing the resources and all that stuff, and the namespace, you're unsharing the namespace from the parent to the child, and then the fork is ensuring that the child's not reading back into the parent. Hope that was kind of understandable. With that, there's also another one I wanted to show here is another namespace for users. So this one's kind of the directory I talked to up here. And this here is going to be around user namespaces. So it's similar to jailing, right? So we're just jailing the user instead of the directory or the user namespace. So here we can see this very top level here is the like the parent, the outer host. So this is our kind of holistic user namespace. Below that we have another namespace. So you can think of this as like your level 1 namespace, or maybe you can actually encapsulate containers in containers. It's like inception basically. So we can kind of use that as an analogy here. So we can say namespace 1 is container 1, and then namespace level 2 down here can be container 2. So we have these two different namespaces. And as you can see here, our root level 0 is going to actually be, in all reality, 1000. And then our top 499 is actually going to be 599. So in this virtual container, we think this is all of our user namespace because that's what we can see. Another level down is we have our 0 root here, which is actually going to be 1000 in this user, which is going to be a different number here, which is in our host. So we can see that the further we go down, the more tight we can become with our namespaces and what our users can actually see. And basically the user IDs they're associated with within their container, and they can't see outside of that. So that's another one that I thought was interesting. Okay, so with that being said, this is kind of like a holistic image that I wanted to show for Cgroups and namespaces to kind of get an intuitive idea of what I'm talking to. So here you can see that we have our host machine, which is going to be our outer host. We have our kernel, right? And then our outer host basically shows that our namespaces for container 1, 2, and 3, this is what they can see inside of outer host, kind of like shown by the dotted line. This is what they can see. And then below that is the resources they're allowed to utilize. So it's kind of contained by this, I think it's a polygon. It's not a polygon. It's not a hexagon. Don't know what the shape is. Probably should, do some geometry. Anyways, so this is basically showing you our Cgroups and what resources they're allowed to utilize from the kernel, the CPU, the memory, all that stuff. So that's kind of the intuitive image of how it all works together. All right, next is images. So images within Docker it's the way I want to explain this is, so an image is kind of like a static template of what the container should look like when it's run. I think that's a decent definition. And with an image, there's some confusion, at least for me when I originally read this and I was reading the terminology around images and containers and stuff, is there's things called makefiles, there's things called images, and there's things called containers. And I didn't really know the separation, the discernment between each one of those and their functionality. So in the book there was some good explanations. I found some good videos, but I also found this image and other images like it that have like a simplistic understanding of what the difference is between each. So a makefile, so a Docker file here, this makefile is basically going to have a series of simple steps of what should occur for the build. So what you're going to do is you're going to take a makefile and you're going to build an image. Once you have your image, then you're going to run your image to turn it into a container. So when you're taking your makefile, you're going to actually run a series of simple steps. Those simple steps are going to build an image. That image is then going to usually be layered with other images. So we're going to have layers of this, which I'll show you what that looks like. And those layers of images are then going to eventually run, and all those images that run are then going to turn into a holistic container. So with images, let's go to the next slide. Here's a simple kind of setup here. So we have our base image, right? So this is our kernel. This isn't an image. This is kind of what we're running on. And then right here, we have our base image. I'm going to talk to some of the importance of actually ensuring that this is authentic and simple. But your base image is kind of the bottom layer. So what OS do we want to run on for this image? And then what's going to happen is we're going to have layers of images. So we're going to have multiple images that are all stacked on top of each other. And each image in the makefile is going to reference the previous image. So usually in a makefile, it's going to say from something and then keep going. And these are all going to be chained together. And that's why this arrow is here, basically showing you that they're being chained together. And as they're being chained together, it's going to then build eventually what is run as the container. So these are the images, this is how they're stacked. And if I go to the next one, this is a larger makefile that's a multi-stage build, which I'll talk to in a later slide. So let's zoom into this to see kind of like the simplistic piece here. And this is what I was referring to, where we have this reference piece for the parent image, so it's referencing something. That reference correlates to this from section here. So we're saying from, node, latest as builder. So we're saying from node, we're going to pull that from the previous one, we're going to stack it onto this. There's a few other things that are happening here. Basically what we're doing is we're saying the working directory, which is going to be our jail directory. So we're jailing you into this directory, saying that from our host outer source under use source app, this is going to be your quote unquote root directory. This is what you're going to see. Within that directory, we're going to copy some stuff into it. So we're going to copy some packages from this kind of location, this source into here. Then we're going to copy our source code into the source directory inside of under app. And then at the end, we're going to run. And the run command is basically going to do an npm install. So that's like the simplistic version of a makefile. So that makefile is then going to build into an image. Then that image is going to be stacked into a container. I regurgitated myself a lot. I hope that's somewhat useful. So this here is a really beautiful image that I found on the Googles. And this basically shows you some of all of the stuff I've discussed previously in like a holistic flow of what happens in all the different pieces interacting. So I'll walk through some of this, and I may have to change my coloring so you can see it. I'll do black. So here, we'll start with these lines. So we have our lines, right? So our lines are going to show what's being, what the process is happening. So we have our build process, our pull process, and our run process. We'll start with build first. So we have our client that can be on, a CLI, or it can be on a remote API or a console or whatever. Most of the time you're going to use a command, and then it's hopefully be automated. But first things first is we're going to run, we're going to build, sorry. We're going to build our image. So we have our makefile. Our makefile is going to run through this build process, and it's going to build our image here. What you can see here is a daemon. So this is the Docker daemon, and it's connected to an API that actually has access to a lot of stuff. It's very dangerous, so you have to be very careful with this daemon, and I'll talk to some pieces about that in the future. But everything's going to run through this daemon for everything to actually get completed for your building and running of the images and makefiles, etc. So like I said, we're going to build our image here. So we built our image, and then our image is then going to be, like I stated, layered with other images. And once it's layered with other images, then those can eventually be run, which you can see being depicted by this green line here, because we're running our image then to turn it into a container. So another thing here is we have our pool. So the pool piece is pulling from a registry. So that registry is basically, kind of think of it as like a GitHub, like a repository with a bunch of stuff in it. And that registry is going to have a bunch of images in it that you can pull, and those images could be public, which they could be under Docker Hub. So Docker Hub is kind of like GitHub, but for Docker images. Or you could have a bunch of images like sitting on a local network or a local machine that you're pulling from that registry. So you could have a local registry or a public registry. And when you're pulling those images in, that's going to kind of give you a baseline to build off of. So here you can see they're pulling in a bunch of images. Those are then being stacked, and then they're being run to create a container. So that is very useful, and I hope that was helpful to kind of get an idea of how everything works together. All right, next, what's the difference between a container and a virtual machine? So the simplistic explanation for this is something you'll see a lot on different videos and articles, is that a container, basically you're bound to the operating system that the Docker runs on. And then a virtual machine, you can run different operating systems on top of that operating system. For example, with a Windows machine, if you had a virtual machine on there like VirtualBox, you can run VirtualBox on top of Windows, and you can run Linux and VirtualBox or other operating systems unrelated to Windows. But with a container, if you're running Windows, you have to run Windows containers. If you're running Linux, you have to run Linux containers. One misconception that I've actually learned when doing this research is that when you run a Linux, when you run containers on Linux, you don't necessarily have to use the same distribution. So you don't necessarily have to run Fedora on Fedora, or you don't have to run necessarily Debian on Debian. You can run Fedora on Debian, you can run Arch on Debian, you can run a variety of flavors of distros on that operating system as long as they have the same kernel, which I thought was pretty cool. So what are the differences between the two? Some of the differences that I found that were not as obvious as I've seen in other videos. So one of them here is the efficiency or the performance of containers. So with containers specifically, there's two things that stand out. One's startup speed and one's execution speed. So we'll first start with startup. So the startup speed is talking to the fact that a container is a lot less bloated, in the sense that with a virtual machine, there's a lot of libraries and packages, and there's operating system, obviously, and a whole bunch of other stuff that has to all kind of work in accordance to have that virtual machine running at the end of the startup. Well, with a container, there's a lot less there, and it should be a lot less, so you can hopefully be a lot faster and also be very specific on what the container's purpose is for. So containers are a lot faster when they start up. That's one. Another thing is the execution. So how fast does it take for an application to execute a process? Well, with a container, they execute a lot faster. And this image here kind of depicts why that's the case. So if I bring you back to my bright pink, this here you can see there's a series of layers here, and those layers are a lot thinner than this one because they don't have a guest OS, but they also don't have a hypervisor as well to go through. So the path from initiating the execution for that execution to actually do its processes with the kernel and back up is a lot smaller. So that execution path is going to be a lot faster. And with a virtual machine, that's not the case. There's a lot more detail to this, but I think that is enough to kind of explain the fact that you're going through less, so you can be a lot faster when you execute things with containers. So that's some of the positives for containers. Another thing is for security. So for security, containers are a lot more complex, so they're a lot harder to secure. So virtual machines, out of the box, they tend to be easier to configure to be more secure due to the fact that their attack surface is a lot less. There's not many variables that need to be balanced and juggled. But with containers, at least traditionally, they were very difficult to secure, and they were out of the box weren't as secure as virtual machines. And the main reason is syscalls. So I guess kind of like a quick breakdown of what syscalls are. So we have up here, we'll call this user land, if I can write. And then down here, we'll call this kernel land. So in user land, you really can't do much with an application. There's a lot of stuff that you need kernel land for to actually get anything done, like reading files, opening files, executing files, all that stuff. So in user land, your application, when it runs, it's running a series of system calls. And those syscalls are bundled in functions, which are bundled in a bunch of other stuff. But when that syscall is run, it's going to have to call down from user land to kernel land to call that specific call it needs to do, such as opening a file, writing to a file, or executing a file. And then kernel land sends a response back and gives them the ability to do so. So as you can see here is currently, from what I could find, there's 494 system calls that are accessible for at least the Linux kernel. And to secure those, you need to make sure that only the system calls that should be called within your container are being called. So you don't want to necessarily allow your container to have access to all the system calls, because if you do, then that's a ripe setup for disaster. I wanted to actually show a quick video here from a lecture that I watched that I thought was really good, that I'll link in the resources, that shows the complexity and just the length of syscalls.
I sure hope I see nodding heads. Yes, that is. It is possible. But it's also relatively straightforward to defend against because the attack surface is narrow. By comparison, the Linux syscall interface is not quite as narrow. There are 397 system calls in the Linux syscall interface.
And the next part of that lecture, when he's talking, is actually talking through this specific depiction here, where you can see between the virtual machines we have a solid line, right? So there's a solid line here and there's a solid line here. But in the container section we have a dotted line. So what we're trying to show here is that the separation between virtual machines sitting on the same host is very clear. There's a very clear line of discernment because, like I said, the attack surface is lower, so it's easier to know what the separation is. The separation of duties are between those. But with containers, all these dotted lines have a lot of gaps, and those gaps are system calls. So it's a lot less clear of where the separation is between each container and making sure that they're not talking to each other when they shouldn't be. So I thought that was pretty cool. Next thing we're going to talk about, the difference between the two, or not necessarily a difference, but something that stands out for containers that aren't necessarily correlated to virtual machines, which is this thing called thinOS. So this is something we talk about in the book where when you run a container usually on an operating system that is made for that container to run efficiently. And that is called a ThinOS. And what that is basically it's an operating system that is stripped down to bare bones, and it's stripped everything out of the operating system except for what's needed for that container to run efficiently and effectively. Here are some examples. Here's one from, I think this one's from Red Hat, which is CoreOS. This one's RanchOS, and this one I think is VMware. And out of these three, I think I've seen this one utilized the most, or at least talked about the most from different people, which is RancherOS. So those are ThinOSs. Another interesting thing that came in the book is called micro VMs. So this is kind of like the next step in maturity for containers. And this is an example from Amazon, which is called Firecracker. And the interesting thing about this is that, like I stated, virtual machines are easier to secure, which is an attractive trait in what people would want with their containers. So what's slowly happening is they're taking virtual machines and they're actually microtizing them. So they're doing something similar to ThinOSs, where they're ripping out everything from the virtual machine except for what's needed for that virtual machine to run effectively and efficiently with a container sitting on top of it. And so much so that Firecracker, when doing performance tests between containers sitting on a ThinOS and containers sitting on a micro VM, the speed and efficiency are very similar, if not sometimes better in the micro VM. So this is seemingly a trend that people are going to start moving towards, where you can get both security and speed bundled up in a setup like that. Okay, so that was containers versus virtual machines. Now we're going to dive deep into securing containers. So I've broken the securing container section into two bits. The first piece is, I think it's build time security. And the other piece is container isolation and a few other things. So for this piece here, the first one, which is the build time security, there's a lot of stuff that was discussed here that I can't or don't want to regurgitate all at the same time. So what I did is I pulled out a few different terms that Liz, the author, referred to quite often throughout much of the book when it came to securing the build time piece of an image when it's going through the process from makefile to image. So here's some of the terms, and here's some of the explanations and high-level concepts for each. My recommendation is to take some of these ideas, anything that stands out that's interesting, research further, and that goes for the whole presentation, but especially for this part. So first thing is the base image. So I've talked about this in the previous, or I hinted at it in the previous slides. So remember, our base image is the thing that sits at the bottom of the layer of the stack, right? And at the bottom of the layer of the stack, we need to ensure when securing our images is that our base image, and all the other images, honestly, we know both. We want one thing and know the other thing. So what we want to know is the authenticity of this image. We want to know where it came from. And one way of doing this is actually pulling the hash or the digest hash for that image. So when you pull an image, remember how we looked at the big architecture graph where we're actually pulling from the registry? So we have a registry, which can be from a public Docker hub or a local location. So in here, a way that you can pull stuff from there is really, there's a command that you run, and that command can include a tag. So you can have a tag in there, or you can have a hash. So there's benefits to both. To be honest, you should use either or depending on your circumstances. Tags are useful because when you pull a tag, you know what you're pulling is actually going to be up to date. It's going to have any patches or any updates to the code. So it's going to be frequently updated because this tag is somewhat of an alias to an image, which is then linked to a hash. So tags are useful for keeping up to date with things. But running a hash and pulling it from a hash, you specifically know what you're getting because you're pulling the hash of the image. You're not pulling a tag that's an alias in front of a hash because you don't necessarily know if this tag is linked to the correct hash. So if you want the correct authenticity of the image you're pulling, especially with the base image, it's important to pull the hash instead of the tag so you know where it's coming from. That's the first thing. The next thing is ensuring that your image is very, very minimal. So the base image and all the images, honestly, should be very simple in nature. So each image should have its own purpose and its function, and you can see this base image here is it's basically setting up the operating system for Debian, and that's the sole purpose. The next one on top of that is adding Emacs. I know people like Emacs, and I know people like Vim, and I know there's a massive war between them. So you can add Vim in there if you want, but you can see it's adding a text editor. The next thing is adding Apache, so on top of that. So you can see that each layer has its own purpose. So ensuring that the base image and all the layers are very simple in nature, and also you know where they're coming from. That's the first thing. Next thing is multi-stage builds. So this is something I've talked to already. or at least hinted at. And in a previous slide, I only focused on this piece here, talking you through kind of what the makefile does. But inside of this, I think this is an example from Capital One. And what this example is showing is that here we have a series of makefiles. And each of these makefiles are going to, this is considered a multi-stage build, because the makefile here is built into an image. And then this is referenced from this one here. So this is referencing here, this is referencing here, and we're going backwards. And as we go through this multi-stage build and we build out each image and layer them on top of each other, each image has its own purpose, functionality, and they all work together cohesively. And I think a better way of showing this, instead of just showing the makefile, is actually this image that I found in the book, which kind of walks you through that process. Here you can see that this stage here, so we're taking the base and we're going to basically build that image. And the purpose of this is to start with the linting process. So we're going to lint and ensure the linting is set up. Next thing is we're going to do static code analysis in the code that we've downloaded and copied. Then we're going to run unit tests on that code that we've uploaded. We're going to run unit tests on that specific makefile for that image. Next thing is we're doing accessibility tests, and then the last part is we're actually deploying that after we've run through all this stuff. And there's multiple reasons why someone will want to do this to make sure it's secure. But one of the main things I found when reading through and watching stuff is that the multi-stage build is important due to the fact that you're breaking things up into simplistic pieces, and you're also ensuring that each step is successful and meets certain requirements before going into the next stage. So it's a way to kind of ensure you're incorporating security throughout the build process of that image from the makefile. All right, next are two things. So non-root users and run. So we'll start with non-root users. So rootless containers is something that she talked to quite a bit as well, and you can see that at the very bottom of this graphic here, which states rootless. And this is something she repeated a lot. So this is probably quite important, or at least a lot of people make the mistake. And the thing that was pointed out most frequently is that when running a Docker container by default, without making any changes, any configurations, any adjustments, or any security implementations, is that it usually runs as admin. And when a container runs as root, that opens up a whole swath of things that could go wrong with your container, especially if an actor gets in there, an attacker, and they could do really a lot of what they want, both on the container and also the host machine that's hosting it, which then they can move laterally and do all this bad stuff. So to run a container as a rootless container, one very simple step that she mentioned is basically taking there's a command that's called docker run, right? So docker run is a simplistic command that starts up an image into a container. So instead of running the default Docker command that's given you from Docker, switch that out as an alias. So take Podman here, and Podman is a tool you can use, and Podman is basically going to ensure that when you run the container, it's run as rootless and not as root. So if you set up Podman and you swap Docker and Podman out as aliases, so if we say D is Docker and we have Podman as P, we're going to replace Docker with Podman. So anytime you run docker run, it's actually running Podman and not Docker. So that's the first thing, is swapping out aliases. Next is I want to walk you through what we're looking at here on this graph. So in this graph here, we can see a few things, and we'll work our way down this way. So first we have a user namespace. So here you can see that we're stating that there is no user namespace. So when we say there's no user namespace, is that we can see that in this section here, our Docker D, and let's actually break this out. So the yellow section is the host. That's the outer host, the machine it's running on. Docker D is the Docker daemon API that I mentioned that has access to a lot of stuff, and it's very dangerous, or it can potentially be dangerous, but it's useful because you need it. And then we have our containers here. And these containers are using our Docker daemon to access the host to do certain things for those containers to function the way they need to, syscalls, etc. So here you can see that our Docker daemon is set up as UID 0, so that means it has root access on the host machine. That's a no-no. Next, we can see our container has UUID, which is linked to this ID, which is linked to the root. So our container is running as root, and that is a definite no-no. And the container B is the same, so you can see it's directly connected to the same user ID space, same namespace, all that stuff. So that's no bueno. So next is the area where we run with a user namespace. So this is like definitely bad. This is kind of bad. This is way better. So this kind of bad one with the user namespace, we can see that our Docker D daemon here is running still as root, and it still has connection to those. So that's not good. Shouldn't do that. But our namespaces for our containers are improved because our user ID root here thinks it's root, but really it's running as user namespace of 110,000 or whatever that is. Same thing applies for container B. That's okay. Now, With the rootless container, we can see that our Docker daemon here, it thinks it's root, but it's really running as 1000. So that is super important and should always be the case for most containers. Same thing applies for container A and B. So that's kind of the process between all of these and the difference. And when running podman, you separate yourselves out. Another thing for the run command that I have listed out here. So really quick for this one, I'll just mention that she mentioned this was important to track any changes or when this is run. So when the run command is run, it should be logged. Reason being is that the run command is very important in the sense that it takes your image and turns it into a container. And depending on the switches that you include in that command or whatever additional items you include there, it could actually lead to disaster. So in the sense that when you run the run command, it should be codified and it should be automated and it should never change. It should be run, Docker container, switch, whatever else you want to include in that command. If there are any variants, any deviations from this template of command that you think the run should occur, that all should be logged, even when it's run normally. So that's basically one important thing, is to always log that stuff. Next thing is mounting. So to quickly explain mounting, as a container, a container should be immutable. And there's a really poor explanation or a poor analogy that I don't like about the container thing, is where basically people say that containers should be treated as cattle and not pets, where you should just kill your containers and then create a new one from images. We're not gonna talk like that. Instead we'll say that containers should be immutable and they should be easily removed and added back. And with a container, say you don't want to necessarily operate on a running container or update it with patches or make adjustments to it while it's running. All those different configurations and changes in state should occur within the image and not the container. So what should happen is you should rip this container down, come back to your image, update your image with new patch updates, with all the stuff that needs to be done through the image. And once the image is updated, that's when you then recreate another container, another instance. So when doing that, the old container that was running may have some sort of data that it needs to persist. So when it comes back from its updates and all that stuff and starts running again, it can actually get that data and keep doing what it should be doing. So mounting helps with that process. Mounting is a way to actually connect your container, mount it to usually a directory inside of the host system, and store persistent data that's needed for that container when it comes back to life. Here's an example, kind of an image that shows different types of mounting. There's a lot more to this, but these are some simplistic ones. The two that I'll point out, one is the volume mount. So let's find our black again. What is it? 9? We got 9. So first we have volume mount here. And the volume mount is very similar to bind, and from what I can read, basically they state that you should use volume and not bind, due to the fact that this is more modern and more, I guess, there's more stuff for it and it's more secure and all that good stuff. It's more, that's why. And with the volume mount, what it's going to do is it's going to basically take your data and have it persist within the file system of the host. And you can see here we have our file system, and we're going to basically say, okay, in this area where Docker stores its data, that is the persistent section where we should pull that information when that container comes back up. And the other thing here, so that's persistent data. This data here is tempfs, so this is temporary data. And this temporary data usually is associated to either data that is ephemeral and should just disappear and has no purpose of sticking around, but also more for security purposes, this is where you should maybe put your secrets if you're not necessarily using a secrets manager, which we'll talk about later, which you probably should use. But if you're not using that, you can store those secrets and things like that in the memory, so it's temporary and disappears quickly. So that's the tempfs mount. And that's the premises of mounting and ensuring that data is set up correctly and secured. And one important point I'll point out about the mounting piece with security aspect is that sometimes people, what they'll do is they'll actually incidentally set up they'll link this container, they'll mount it to a location that it shouldn't be mounted to. So when you mount the container to the file system of the host area, make sure you mount it to an area that's dedicated for Docker and nothing else. Because sometimes when people mount their containers, they might actually mount it to a file system or a parent file of a directory that has sensitive information in it. So if an attacker gets into your container, then they can actually go into your file system, grab the secrets or grab whatever sensitive information in there, or escalate their privileges and gain access to a lot of stuff they shouldn't. So that's one interesting thing about securing this, is making sure you're mounting it to the right location and mounting it to the right place for that dedicated area. All right, next, I made a video on the CTF. There's a CTF that I made recently. I'm going to put like a video here, or I'll point to it somewhere that you can actually learn more about specifically the SetUID bit and why it's dangerous and why you should try to avoid it for your files. I will actually quickly show what it looks like here. So you can basically have a file and its permissions, and in those file permissions, usually it's RWX, which is read, write, execute. But sometimes those permissions will set with a lowercase s, which is setting the SetUID bit. And if you do that, then you could potentially give an attacker temporary privileges when that file is either being executed or else. And when doing that, they can actually get temporary privilege escalation to do other things and get access they shouldn't. So this is not a container-specific thing, but it's something that I wanted to point out because I made a video about it, and you should check it out. And it was mentioned in the book. All right, last is less is more. So this is also not a code-specific thing, or not code, container-specific thing. And the reason being is that less is more with containers. When a container is running, it should have all the code it needs within the image before the container is run. So when a container is run and created, there shouldn't be necessarily additional libraries or packages that it's pulling down after it's been created. The image itself should have all the information it needs. So when the container is run, there's no additional steps happening here that are unexpected or you're unaware of. There could be additional steps that are needed for things to execute and things like that, but everything that is needed for that container to do its job should be baked into that image before it's run to the container. So that's the less is more piece that Liz has mentioned a lot in this book. So ensuring that the code is minimal and there's no additional cruft that you're unaware of. And the last piece here, actually, all these steps here I've talked about for the build time, I think it's build time, right? Yeah, build time security. With all these steps and many of the other stuff I'm going to talk about, there's this thing considered GitOps or DevOps or DevSecOps or all the different acronyms smushed together. It's a simplistic way of basically stating that, or a convoluted way of stating that all these steps should be manually tuned, and you should know all the steps and how they're well defined. And after that, you should codify all of it. You should codify all the logic so everything is automated, and there's very little human interaction, if not any human interaction. We should try to prevent all human interaction with it. So it's all repeatable, it's all sustainable, and it's all scalable. And you know exactly what's going to happen. And that's kind of the GitOps thing that she wrapped around all these things in here in the book. This is a simplistic image that she provided to kind of walk you through what the steps would be for the high-level steps and how all that should be codified, and there should be no human interaction. I'll talk to the top piece here simply because we are dev, so we have our source code. All that stuff's going to be then posted or committed to the Git repo, right? So this is going to have some human, right? And then we're going to have a little bit of automation. This should be automated, right? Because we have our Git credentials. It's put in the code repo. Unless there's some static analysis checks from other people looking at the pull requests. Here we have our credentials. So this is going to be the building process. This should be fully automated. Our registry credentials are going to be sitting here. So our registry credentials for the images, etc. That should be automated. And then we have our orchestration, which is, I think this is like Kubernetes stuff. I've run into some Kubernetes that I tried to avoid because we're looking at containers today and this week. So we'll look at that later. But, long story long, you should actually automate most of this through the GitOps process. All right, the next thing is we want to talk about immutable containers, container isolation, and runtime protection. So first things first, we'll talk about the immutable containers. So I've already talked about like the pets and the cattle and how you should rip them down, change the images, and then put them back up. Already talked about that. So specifically, I want to talk about the images, how we can maintain and secure these and ensure they're set up to a good stance so we can actually run the containers in a good fashion. So immutable containers. So the image that she showed and she talked through was one of the important pieces of containers is actually scanning images. So the images that we've built from our make files, those should be scanned at multiple phases of the building process, and they should also be scanned consistently when they're sitting in the registry. So here I have a few things I'll point out. Down here we have two logos, and this is a reference to tools that can be used for scanning images for vulnerabilities. I think this is called Trivy and this is Anchor. The author works at a place called Aquo, so she kind of sponsored some of her products inside of the book, which is totally fine. Most of it wasn't an advertisement, so it's okay to slip in some sponsorships there every now and then, or advertisements. So these tools are used to scan images for vulnerabilities. These are the three locations that we want to consider scanning. This first step here is when our developer is basically taking the make file that they've created and then they're going to run it through the building process. So as soon as that developer makes that file and they commit that to the build process, we should scan that image. We should scan it for basically any vulnerabilities that have been newly updated. So actually, one thing I should probably take a step back, and there was actually a really good point that Liz pointed out with these logos here, is that any of the tools that you use, even the ones that she advertised, they have false positives like any other tool. Some of those false positives will be basically that maybe a vulnerability database was, they're pulling from a specific Vuln database to actually scan your images for. Maybe they're limited on the sources that they're pulling from. So maybe they should, one tool is favored over another because of the sources of breadth that it's pulling from the vulnerabilities. Another thing is that maybe the make file you have references a package that it wants to pull down. Well, maybe that package has a series of sub-packages that you're not necessarily utilizing. So maybe you have a parent package here, and that package has a few different sub-packages. But maybe you're only using these packages here, but when the Vuln scanner scans your image, it's going to see that you're referencing this package, so it's going to assume that you're pulling all the sub-packages. And when it does that, there's a chance that there's going to be a false positive because it's saying, oh, well, this sub-package here has a vulnerability, but in all reality, you're not using this one. So that's another way of getting a false positive. So there's many ways of getting false positives, so it's important to know that that exists, and that's the thing. Back to the main story. So we're scanning when our developer commits their make file to the build process. We need to ensure that this has no vulnerabilities in it. Next, we're going to scan during the build process when we're going from make file to image and ensure that there's no additional vulnerabilities there. And now when we're scanning here, another thing we're going to do is after we scan during the build, and actually this isn't during it, it's immediately after. So when the image is built, so when the make file is built into the image, we're going to immediately scan after that's built to make sure there's no additional vulnerabilities or any vulnerabilities that have creeped in through that process. And then the last one is actually continuous scans. So this one is usually, she stated that it should be a 24-hour basis is kind of like best practice. So scanning these images every 24 hours and also anytime a new image is put in there. Because sometimes you'll have a series of images in your registry that have been sitting there for days or weeks and they've not been scanned. So there may have been new vulnerabilities that have come up in association to those images that you need to scan and kind of be notified about, or there could be changes that happen to an image over time that you've not scanned and you want to continuously scan. So this registry is a continuous scan point. And this one here is admission control. So this isn't necessarily scanning, but this is kind of red light, green light, go, right? So when you're taking your image and you're going to run it through deployment, this is kind of like the last line of defense before it's put into production or put in deployment and run as a container. So when you're going through this piece here, you're going to have a series of basically policies, and those policies, you're going to basically say, okay, this images that I'm deploying, is it compliant with the policies that I've set up when it comes to security? If it's not, then we're going to fail that, and we're not going to allow it to go, or we're going to let it go. So that's the kind of like the last line of defense there through the image process. The next thing is actually container isolation. So container isolation both includes syscalls, which I've kind of called out here, but also includes file permissions and executables and what you're allowed to execute with a specific application, what files it has access to, etc. So the first thing we'll talk to is eBPF, which is Extended Berkeley Packet Filter. And the reason I remembered that is because I have the notes here and I'm cheating. All right, I have a quote that I want to read. So eBPF does to Linux what JavaScript does to HTML. So JavaScript makes the HTML website dynamically programmable and adjustable. eBPF does the same thing for the kernel of Linux and other kernels. And it's basically allowing you to utilize the kernel in a programmatic fashion. So with eBPF, we can actually take the container that we want to monitor, run that container in a perfect condition. So to say like the image is set up, everything is done, and the container is running the application the way it should. We can actually monitor and detect all the syscalls that are run within this container, all the syscalls that occur. We can take all those syscalls, then package them up into like somewhat of a profile or a fingerprint and say, okay, this specific container is only allowed, so whitelisting certain syscalls allowed to do a certain thing. And if any syscall goes outside of this whitelist, then we're going to block those and not allow it because it's not fitting the behavior we expect this container to do for its normal functions. So that's one way to actually isolate your container. Another way is actually through, like I stated, file permissions and execution access, etc. So here's a really cool blog that I found that talks through this process. And the two main uses for this, and I'll actually go to the next one, is SE Linux which is one way of doing this, and then there's AppArmor, which is another. I found that more people are actually using AppArmor because it's easier to kind of keep management over because it's simpler, and also it's file agnostic. So SE Linux is only it does most file systems, but there's certain file systems it's not compatible with. So AppArmor tends to be the more modern use. But for this example, we're going to use SE Linux because that was in the blog. So here, we'll start with our dog and our cat. So these are types of processes that we're allowed to run. So think of like applications. And these applications have access to certain objects. And with all that stuff mixed together, we're basically saying that a certain process type or application has access to a certain object type, and those two things are allowed to take this action. And we're saying this allowed here. So we're saying that this cat is allowed to eat cat food, and this cat is allowed cat food, and it's allowed to eat it, basically. Same thing applies for the dog. So if we mix any of these process types, so if we have a file that says, this application has access to this file, and it's allowed to do these actions on this file, that's kind of the profile that we're setting. So with our application that's sitting in our container, we're both containing the syscalls, but we're also isolating the application's ability to access certain files and do certain actions on those files. And that's done through these two options here for SE Linux and AppArmor. And then the last thing is actually there's a series of applications and series of tools you can use for this process to simplify it. Liz talks about Tracy, which is a product that her company runs, but there's other tools that can do this. And Tracy is this little cool logo here. Props to them for having cool logos. So this cool logo here is called Tracy. And what Tracy can do is a series of these steps here. And this is called runtime protection. And runtime, right, we're going from image to container, and that's us running something. So that's runtime protection. And here what Tracy can do is a lot of what we're doing here. So Tracy can basically encapsulates eBPF. So we're able to actually fingerprint, which is why I put this fingerprint here. We're able to fingerprint the container and say, these are the syscalls you're allowed to make. This is the type of traffic you're allowed to actually have go in and out of the network. So for this container, what traffic can go through the Ethernet port or the network interface card. The other thing is you can actually do the same thing for the file permissions of the application. So these are the certain access and type of access and type of actions they're allowed to take. And we're actually to take all these different things, encapsulate it into a fingerprint for that container, and say these are the things this container is allowed to do. And if anything goes outside of this whitelist, then we're actually gonna cancel it out, and it's not allowed to happen. So tools like this, Tracy, help a lot of this process be simplified and not become more robust, because obviously that's what technology companies do. So that is securing the container. That's it. Those are all the steps, So maybe next time, right? These are some of the things I wanted to talk to around things that I wanted to dive deeper into in a future life. So this one here is sidecar containers. That's what it was. So we will go to 9, and look at me getting good at this. So sidecar containers, what are they? So within a fleet of containers, each container has its own purpose. They all have different variations and functions. Well, we have these things called sidecar containers, which are very similar to base images. And the way I want to explain this is that, remember how we talked about our images, right? And our images were layered. And each layer has a specific purpose. But the thing is with these layers, with base images, say we have our base image down here. Well, maybe these layers here for these images are all things that all the other images need to use. So if we have all these image layers here at the very top, they're all going to borrow from this base. So it's kind of like classes and objects in programming with object-oriented programming, where you have a class, and that class then can create objects, which inherits certain things from the class. Another way of explaining it is kind of like genetics. So you have your parents, and those parents have certain genes, and those genes are then passed down to you that you inherit from them. So that's the image piece, but why does this fit into the sidecar piece? So sidecar containers have functionality that are adopted by other containers that aren't necessarily those containers' jobs to do, because this sidecar can have a dedicated purpose, such as networking, such as logging specific security events, such as other things that all the containers need, but none of them need to use themselves, because we can run it all through our sidecar container, which has that specific purpose and functionality. And in this this specific example here, we have our main container, right? Because so these main containers, they have specific purposes and specific functionalities. we've already talked about volumes and mounting. So you can see what we're doing here is we're taking this main container, we're mounting onto this, and this volume looks like it's taking log data, and that log data is being stored in the file system that this sidecar container has access to. Because the sidecar container's job is, sole purpose is to log information for certain events. So what the sidecar is going to do, container is going to go into the volume, grab those logs, pull it out, and then put it into your aggregator. So it could be some sort of SIM, like Elk Stack or Splunk or whatever else. So that's the purpose of a sidecar container. This is just another image of showing that same process. So we have our main container, right? It's pulling stuff into the volume that it's mounted to. This log side container is pulling that out and then throwing it into your aggregator for you to look at and make pretty visualizations. So that's the thing I want to look into in the future. Interesting topic, very relevant for Kubernetes and mesh networks and stuff like that, but not today. Next thing is key management, so secrets, managing secrets. This is a logo of HashiCorp, and HashiCorp has a dope logo as well. I'm always a big fan of dope logos. If you got dope logos, you get respect from me. So this is a topic I want to discuss. What I'll share here specifically that I read in the book that I thought was interesting is that with key management, most of the time you should always outsource it to a key management services. Usually big cloud providers have it. There's third-party providers like HashiCorp that do it. Reason being is that they can help with a lot of things. One of the most important is actually rotating those keys consistently and ensuring that they're encrypted in the right way, in the right manner, at the right time. And also that the rotation of those keys aren't necessarily impacting your containers because they're disassociated from each other. So you can rotate the keys without having to mess with the certificates in the containers. So that is a really important benefit and purpose of using these. That's all I'm going to say on it because I'm not informed on that topic, so I need to research it more. But that is another one that she talked about that I thought was interesting. And another one was mutual TLS between containers, ensuring that the encryption between the containers is exclusive to those two, and there's mutual agreement. But like I said, different time. Resources. So tons of resources here. I'm not going to talk about everything here. I'll talk about a few of them. So this one is a really good, video that talks to I think it's 15 minutes that explains what a container is at a high level. They do a really good job at explaining kind of the whole architecture in simplistic form. This one is a good one that talks about the difference between virtual machines and containers. I really appreciated this video, and this is the one that I learned a lot about the differences, about the not so obvious differences. I'll skip that one and skip that one, this one, and this one. This one is interesting where Liz talks about eBPF, and she actually, I think the really cool thing about Liz, the author that wrote this book, is that she actually, the way that she learns things is she builds them from scratch. So she built containers from scratch and made a lecture on that, which is really interesting. She basically did a guide to syscalls through Go, where basically she wrote some of her own syscalls and played around with the kernel a lot. Here she actually built some of her own Berkeley packet filters. So she's building everything from scratch to learn, and she's teaching you. So I thought that was really cool. This is for the syscall kind of profiling. And this is a guide that I will maybe use someday in the future, which is for Kubernetes, but Docker's inside of it. And it's basically a hardening guide that you should definitely leverage if you're doing anything with anything. CIS Critical Controls, the CIS group, they have these hardening guidelines, and they also have images that are already created, which is really cool, where basically you can actually take a pre-hardened image, pull it down from a registry that's publicly exposed, take that image and then run that, and knowing it's secure. That's maybe another video that we'll make together. But with all that being said, that's the video. This video is probably really long, but I hope you enjoyed this, and I'll see you next time.